So this is the 2015 probability question. It was worth 65 marks. A couple of tricky parts to it, but overall not too bad. We're given some information. When Michael takes his first free throw in any game, the probability that he is successful is 0.7. So first free throw. I'm just going to jot that down here. First free throw. The probability of success is 0.7. Probability of failure will be 0.3. What are we told next? For all subsequent free throws, the probability that he is successful is determined by whether he has been successful or unsuccessful on the previous throw. So 0.8 if he has been successful, so the probability of success 0.8 if previous was S, and 0.6 if unsuccessful. So the probability of success is 0.6 if not successful on the previous. So find the probability that Michael is successful with all three of his first three free throws. So probability of success in the first one, 0.7. But he was successful, so it's 0.8. So 0.8 by 0.8. 7 by 8 by 8 is going to give 448. So 0.448. The next one, unsuccessful UUS. So unsuccessful with first two and then successful. So unsuccessful is failure on the first. That's this one. So that's 0.3. He was unsuccessful on his previous. So the probability, we're looking at not successful on previous. So the probability of success if not successful on previous is 0.6. So the opposing side of this, the probability of failure is 0.4 if not successful. So that's 0.4. And now we've gone from not successful to successful. So this is this one here, this 0.6. He wasn't successful, not successful. So the probability of success is 0.6 on his third one. And 12 sixes are 72, so 0.072 is going to be the second one. First one, 0.448. Third one, list all the ways Michael could be successful with his third free throw in a game. So all the ways he could be successful, so we have to have S at the end, and hence find the probability that Michael is successful with his third free throw. So what way? We've already got two of them done. We have SSS. So they're setting up the question here. US. So this has to be S. There's not that many combinations. It can either be SU or it could be US. They're the only two left. So we have the first two. SUS, so successful on his first, was 0.7. From this 0.7 here, you can see. So unsuccessful, haven't been successful, we haven't come across yet. So let's just go back up. So he was successful. So the probability of failure comes from this one. He was successful, that's this S. He was successful, 0.8 to shoot it in again, but so it's 0.2 to miss. And then this US we have had here. So if unsuccessful, success to follow that is the 0.6 from above. 0.6. 6 twos are 12 and 7 12s are 84. 0.084. That's our third option. I think we're going to have to add these together in a minute. Our fourth one, USS. Okay, well, we've had this one before. Unsuccessful to begin with was here, 0.3. Followed by success. Well, that's this success here, followed unsuccessful. So that's this 0.6. So by 0.6. And then successful, having been successful on the previous one, is this 0.8. And 6 8s are 48, and 3 48s are 144. So that's 0.144. So I think it says, and hence find the probability all along here. Find the probability Michael's successful with that third free throw. So you just have to add these numbers together. 0.448 plus 0.072 plus 0.084 plus 0.144. They all give. They add up to 0.748. 74.8% chance if you were asked for percentage, but we're not here. Okay, on to the next part. Let Pn. Now, I had to snip this, it's a little bit blurred. Apologies for that, but if you want the whole question done in one video, that's the way it has to be. And this Pn is probability of success on his end. So let's take that this is the end. Let's take this as the end. The probability of success is Pn. So the probability of failure, both of these numbers add up to 1 minus Pn. That's success. And that's failure on his end. Okay, what else is going on here? They've given us, show that the probability of success on, this is Pn plus 1 here, is equal to 0.6 plus 0.2 Pn. So this is success on the next one, the n plus 1. So the probability of success on the n plus 1 we have to show is 0.6 plus 0.2 Pn. So we're taking this nth one. What has happened here? So we could have been successful. So for the n plus 1, we could have success previous to it, or we could have failure previous to it to be successful. So this is my n plus 1. This is n plus 1. And this is n up above. So what can we fill in here? Well, we have the probability of success preceding something or following something. So we can bring that in here, and we can use these two things that we're given, and hopefully we'll end up with what they asked for. So we need to know what was success. What was this success? The probability of success following success. Well, we have it in the first one here. You can see success following success, and the third one is 0.8. This 0.8 here and here. So success following success is 0.8. So that's this one. So 0.8 times the probability of success on the end was this Pn. So 0.8 times Pn is S followed by S. And we have success followed by failure followed by success. So this success here. So we need the probability of success that followed failure. Success that followed failure. You can see it here. Here's a success that followed failure. Here's a success that followed failure. They should be the same number. And you can see in this one, it's 0.6. And in the one up above, it's 0.6. So success that follows failure. Failure followed by this success. This one here is 0.6. And this one here, this F up above, failure, is 1 minus Pn. So if we add these two together, we're going to get 0.8 Pn plus 0.6 by 1 minus 0.6 Pn. And you can see we've like terms here, even though it's in terms of Pn. So we've 0.8 minus 0.6 is 0.2. Pn plus 0.6. 0.2 Pn plus 0.6 is what they're looking for up here. Great. Okay, assume that P is Michael's success rate in the long run. That is, we know for large values of n, we have the probability of n plus 1 approximates as these two lines to Pn, which approximates to P in the long run. And we're asked to show that this P is 0.75. So if all these things approximate to each other, the information we had previously, this guy, we can say, is equal to Pn. So Pn equals, so we can see here, we've identified Pn being equal to this, so we only have one unknown here. So if I bring 0.2 Pn to the left, I'm going to have 0.8 Pn equals 0.6. I'm dividing across by 0.8. 6 over 8, or 0.6 over 0.8 is 3/4. So in the long run, the probability of success is 0.75 or 3/4, which is what you're asked up here. Now, I'll just write this out again. It says for all positive integers n, let an, you have the papers open in front of you, equal p minus pn. And it says p is this 0.75 is above, and it says use the ratio an plus 1 over an to show that an is a geometric sequence with a common ratio of 5. So a bit of a jump in this question into geometric sequences. But if we have an here, this is an. What's an plus 1? Well, n has just changed to n plus 1. So it's going to be equal to p minus p n plus 1. So if I change this fraction here into p minus pn plus 1 over p minus pn, I'll make it some sort of ratio here. So what have I got? We have p, we just got p to be 0.75. So I can change the p to 0.75. pn plus 1 we had up here. This was pn plus 1 from one of the previous parts. This guy. 0.2 pn plus 0.6. So that's minus 0.2 pn plus 0.6. And then that would be divided by 0.75 minus pn. And you can see here now we just have in terms of pn here. So I'm just going to come down to the right hand side here. On top we have 0.75 minus 0.2 pn minus 0.6. So you can see that's going to give, I'll leave out the bottom line for a sec. So this is the top. That's going to leave 0.15 minus 0.2 pn over 0.75 minus pn. So can you see the relationship here? We have 0.2 and we have a full one. So that's a fifth, a 1 over a 5. And there's something about a fifth in the question here. If you remember, common ratio is a fifth. So let's see what we have here. We have, if we factorize the bottom to get the top, let's see can we can do that. It's a bit of a jump here, but if you factorize out on the bottom 0.15 minus 0.2 pn, the top part. So here's the top part, 0.15 minus 0.2 pn. What do I have to multiply the bottom by to get back up to 0.75? 5. And what do I have to multiply the top by to keep it the same? 1. So you can see I can factor out the top and I'm left with 1 over 5. And that proves what we were asked to show, that it was a common ratio with a fifth. So now down onto, looks like a log question, smallest value for n, for which p minus pn is less than 0 point, and there's 4 zeros there, 1, 2, 3, 4, 1. So there's a bit of a jump into this question. Always look back to the previous part of your stuff. P minus Pn is equal to An, which we've just shown is a geometric sequence with a common ratio. So we have a little bit of a knowledge here. An is a geometric sequence with a common ratio, and a geometric sequence can be written in the form AR to the power of n minus 1, where A is the first term and R is the common difference. So we actually need A here. So it's a bit of a jump to go back from P minus Pn to An to realize we actually need the first term here. And this is where this P minus Pn comes in. Because what is P? So the first term here, I'll just jump down to here. The first term, A1, is equal to AR and that'll be AR to the power of n minus 1 or 1 minus 1, which is 0, which doesn't help us get A. So we have to go back to here. P minus Pn. So An is equal to P minus Pn. So the first term in terms of P is P minus P1. Probability of success on the first free throw, which I think was 0.7. Just double check. Always double check. 0.7. So And we also got P to be 0.75. So the A1 here, the first term, is 0.75 minus 0.7. So the first term here, A1, or A, not the first term, A1 here, the first term is 0.05 of this geometric sequence, nothing to do with the basketball throw, of course. So we have A1, sorry, we have A here to be 0.05, 0.05, just come down to here. And we have R to be 1 over 5, which is 0.2. You could write it as 1 over 20 by 1 over 5 if you so wish. So 0.05, 1 over 20 here by R, which is 0.2 to the power of n minus 1 has to be, we're asked for it, this P minus Pn has to be less than 0.0001. So if we go 0.2 to the power of n minus 1 has to be less than, well, let's just divide that in a calculator straight away. It's going to give me 0.0030 So logs n minus 1 by the log of 0.2 has to be less than the log 3 zeros and a 2. So if we're dividing by the log of 0.2, which is negative, we're going to have to reverse that symbol. N minus 1 is greater than the log of 3 zeros and a 2 over the log of 0.2. So n minus 1 is greater than. So that's going to give 5.29. N minus 1 is greater than 5.29. N is greater than 6.29. So n in this case must be equal to 7. So n, what were we asked? Find the smallest value for n. Yeah, and n needs to be a natural number. So you arrive at a game Michael is playing, and you know he has already taken many free throws, but you do not know what pattern of success he's had. Based on this knowledge, estimate, or your estimate of the probability. Well, that goes back to they gave an easy part in here. Look at that, at the very last part of the question. Most people would have given up at that point. 0.75 is what we got in the long run. In the last part, why would it not be appropriate? So they're telling you the answer to consider Michael's subsequent free throw a sequence of Bernoulli. Well, they're not independent. The probability of success and the probability of failure change. That can't happen in Bernoulli. That's enough for that. So that's that whole question. Attempt number 2 there.